What does equilibrium constant tell us? Well, we already kind of talked about this in the last slideshow. Um, the magnitude of the equilibrium constant tells you how far forward the reaction goes. Did you lose a lot of reactants, make a lot of products, right? These are reversible reactions, so they don't have to go far forward. I mean, once you start building up a certain amount of product, um, with certain reactions, the reaction stops quick. As soon as the products start reacting with each other and the reverse rate of reaction equals the forward, you end up with a lot of reactants left over and very few products made. So as long as the K value is greater than 1, this means when the reaction stops, you're going to have more products than you have reactants. So they say it's product favored. A small K value is less than 1. So if the K value is less than 1, it means when the reaction stops, you've got more reactants left over than you made products. So the term spontaneous and non-spontaneous. A spontaneous reaction is one that makes a lot of products, very few reactants left over. Non-spontaneous, the opposite. Very few products made, a lot of reactants left. So our example before, 25 degrees Celsius, dinitrogen tetraoxide turning into nitrogen dioxide. When this reaction goes to equilibrium, and we plug the concentrations into the law of mass action and solve, we end up with a K value less than 1. So, I mean, you can look at it, right? We have a lot of reactants left, very few products made when the reverse rate of reaction is equal to the forward rate of reaction. So, small equilibrium constant tells us this was a non-spontaneous reaction. All right, reactant favored. All right, predicting the direction of the reaction, we use this tool called the reaction quotient. It's just the law of mass action, and what you're doing is taking concentrations of the reactants in the products, plugging the law of mass action, and checking, am I at equilibrium or not? So it's just products over reactants raised their stoichiometric coefficients, and you plug the concentrations that you have in during the reaction and compare. How does Q compare to K? Well, if Q is equal to K, well, those are equilibrium concentrations. You know, the reaction is stopped and you're at equilibrium. If Q is greater than K, it means that you've gone too far forward. You have too many products and you've got to shift backwards and make more reactants. If Q is less than K, it means that you haven't gone far forward enough, right? There's still reactants to lose, still products to make in order to get to equilibrium. So this would be a typical problem. You know, is this system at equilibrium? You know, or is it going to shift towards the products or shift toward the reactants to get to equilibrium? So with these concentrations that were given, we plug in the law of mass action. Products over reactants raise their stoichiometric coefficients. So I plug in the concentrations I'm giving and I compare Q to K. So the value I get with these concentrations is less than K. So no, I'm not at equilibrium yet. I still have to lose more reactants, make more products in order to get to equilibrium concentrations. So using reaction quotient, we'll have some problems to do with those. All right, so calculating equilibrium concentrations. This is the big thing we want to be able to do. So with an equilibrium constant of 54.3 at a certain temperature, the question is, if I start with a certain concentration of the reactants, can I figure out or calculate what the concentration of those reactants and products is going to be when the reaction stops? So hey, I've got all reactants here, I'm going to lose reactants, make products. Now in the old days, when we were doing stoichiometry problems, we just assumed that all the reactants got used up here. Right, so if I have 0.5 moles, say, of hydrogen and 0.5 moles of iodine, we'd go to 0 and we'd make 1 mole of HI. Right? The coefficients tell me for every I lost, I'm making 2 HIs. Well, we have a reversible reaction here. So the question is, how much of the reactants are we going to lose, products we're going to make, before the reverse reaction takes over and stops the reaction? So let's call it X. We're going to lose X amount of the reactants and make 2X amount of the products. So for every X amount of hydrogen, X amount of iodine, I'm going to make 2X amount of HI according to the coefficients. So when the reaction stops, my equilibrium concentrations are going to be 0.5 minus X for the hydrogen, 0.5 minus X for the iodine, and 2X for HI. So these are my equilibrium concentrations now. I can plug them into the law of mass action, right? 2X stands for the concentration of HI. I square that concentration. And I have the concentrations of the reactants both raised to the first power multiplied by each other, and I set that equal to the equilibrium constant. All right, so now the hard part is really just doing the math to solve it. All right, so we have a trick we can use here. Looking at this, if I take the square root of both sides of this particular thing, since it's 0.5 minus x times 0.5 minus x is the same thing as 0.5 minus x squared. If I take the square root of both sides, I get rid of that squared term in the numerator and one of the 0.5 minus x in the numerator. Now, taking the square root of 54.3 is a number. So now this makes it a lot easier to solve, right? So if I multiply both sides by 0.5 minus x, I now have a situation where now I can collect terms. So if I add 7.37 to both sides, I now have a way of solving for x, right? So if I divide both sides by 9.37, I can solve for x. And now I can figure out what my equilibrium, the actual number for my equilibrium concentrations are going to be for the reactants and the products. So take x, subtract it. Well, I mean, hey, the K value, 54.3, is a spontaneous thing. So I expected to lose most of my reactants and turn them into products, which is what I did. All right, here's another one. What is the concentration of hydrogen if I have 1 molar acetic acid? And I know what the K value is for acetic acid. All right, so hey, we had 7 strong acids where we looked at it as though it was a complete ionization. We lose all of our acid in terms of turning into H plus ion and its conjugate base. So in this situation, this is not a strong acid. It's a very weak acid, right? It has a very small K value, very non-spontaneous. So it's the same thing. I'm going to lose X amount of my acetic acid, and for every X I lose of acetic acid, I'm going to make X amount of H plus ion and X amount of acetate. Well, it's a very non-spontaneous reaction, so X is very small, so I'm not changing that initial concentration very much. So if I take these concentrations at equilibrium, X, X, and 1 minus X, plug them into the law of mass action, X times X is X squared, and 1 minus X is the concentration for the acetic acid. I set that equal to the equilibrium constant, and I solve. Now, this would be a hard one to solve for if it weren't for the fact that the K value is so small. So in this situation, what I can do is ignore how much I'm losing of the acetic acid. I'm barely losing any. It's 10 to the negative 5 in terms of a K value. So if I do that, it makes it a lot easier to solve. So I make the assumption that X is really small compared to my 1 molar concentration. I can do this as long as I don't have an error greater than 5%. So I'm going to get a little bit of error, but it's going to make it a lot easier to solve for. So X, as long as K is small, that means, and the concentration of the reactant was large enough, this isn't so bad. I can make this assumption that the concentration really isn't changing for the reactants. So now it's 1 divided into X squared is equal to 1.8 times 10 to the negative 5. So multiply both sides by 1 is 1. Take the square root of both sides, and I solve for X, and I get my H plus concentration. And if I wanted to check this, right, I mean, the concentration is 0.0042. If I compare that to what my original concentration was times 100, yeah, I've got a small error here, right? I got a fraction of a percent error. So this is okay. All right, solving for the equilibrium concentrations for this problem, right? So we have different amounts of hydrogen and fluorine, right? 1 molar hydrogen, 2 molar fluorine. Again, if we were looking at this as a stoichiometry problem, the limiting reactant would be the hydrogen. but this reaction doesn't go to completion, right? Well, you know, it goes pretty close, man. It's got a big K value, right? 115 at 430. Nonetheless, what we want to know, maybe it's imperative that we know how much fluorine gas is left at the end of this thing. So we've got to solve for the equilibrium concentrations. Okay. So in this situation, yes, for every X amount of hydrogen we lose, we're going to lose the same amount of fluorine, and we're going to make 2X amount of the hydrogen fluoride according to the coefficients. When I plug these concentrations into the law of mass action, right, 2X is the concentration for HF. So it's 2X squared over the concentrations of hydrogen and fluorine, each raised to the first power. We can see right off, we can't make the assumption that X is going to be small. It's going to be big, right? We're losing most of our reactants. So if I made this assumption and solve for this, I'd end up with X being equal to 7.58. That's a 379% error. So I can't do it. So I can't make this assumption with this problem. So what happens is we get stuck solving for a polynomial. So if I multiply both sides by 1 minus x times 2 minus x, I end up with 115 times this is equal to 4x squared. So if I collect terms, all right, multiply first, outer, inner, last, I get an expression. And I want to solve for x, right? So I collect the x squared term, add it to both sides, and now what I want to do is solve for x using a quadratic. So I plug the a term, the b term, the c term in for the quadratic and solve. I get x, which is a reasonable answer, and x, which is an unreasonable answer. It's unreasonable to assume that I'm going to lose 2.4 because I don't have that much. So x is my value. These would be my equilibrium concentrations, and I'd be done. In college chemistry, you know, you're made to at least solve one quadratic on the test. On the AP exam, it just takes too long, so we're not going to spend a lot of time solving quadratics. We're going to either use the trick where we can take the square root of both sides to make it easier to solve for, or we're going to have problems where we make the assumption that x is small compared to my initial reactant concentration. Like I said, on the AP exam, you just don't have time for solving quadratics, so you don't see them.